So now that we've seen what a log function is algebraically, we can actually build a model. We can model data sets using logs. So if the data set is increasing and it's nonlinear, we would look at the concavity to determine which model is appropriate. And exponential growth functions are concave up. Logarithmic growth functions are concave down. So what this actually looks like, right, an exponential growth function grows like this. A log function's growing, but more slowly. So this would be exponential, and this would be log. So if you see a function whose data values are growing, and it's not linear, well then, are they growing very rapidly? That would be an exponential model. Or are they growing pretty slowly? That would be a logarithmic model. If the data set is decreasing non-linearly, then both exponential and logarithmic decay functions are concave up. So an exponential decreasing function we've seen looks like this, but a logarithmic function looks like this. So the only way you know here which one's more appropriate is to build both models. And there's three things you can do. You can compare the SSE values, which takes a really long time in the calculator to build the sum of squared errors, and the smallest SSE is the best model. You could compare their average errors, and you want the smallest average error. But once again, that's an extra step in addition to building the sum of squares. Or the easiest way to do it is compare their R squared values. The ones with the largest R squared is going to be the best model. So I actually recommend this method because if you're not actually asked to calculate the SSE, it's a multi-step process that's not necessary, but R squared pops right out of the model when the model's given. So let's figure out which is the best type of model for this data set. So we're going to build an exponential model, we're going to build the logarithmic model, and we're going to compare their R values. So for the exponential model, just so we're ready when we write this down, it's going to give us two data points. It's going to give us R squared, and it's going to give us R. The logarithmic model, we're going to get an R squared and an R, and we're going to see which one's best. So let's build the exponential model first. So the first thing we want to do here, oh, batteries are low, is we're going to go to Stat, List. I'm going to clear these lists. I hope my calculator survives this. All right, so I'm going to put my X values in. It was 2, 12, 22, and 32. Then we're going to go over and put the Y values in. So 186.71, 98.06, 69.06, 56.23. So there are my X's and Y's. So just like always, we're going to go to Stat, and go to Calculate, and I want to find my exponential model. So my exponential model is right here, exponential regression. And we're going to go second L1, comma, L2, and here's our model. So the model, we're going to write this down. The model I'm getting is Y equals 179.746 times 0.961 to the T. And down here on my table, I'm going to write down my R squared value was 0.9407, and my R value was negative 0.9699. So now we're going to build the the logarithmic model and see what happens to the same data set. So now I just go to Stat, Calculate, and if you scroll down, just before exponential model is natural log regression or logarithmic regression. So now we're going to hit that, and we don't need to re-enter the data set. It's still, oops, keep hitting Y equals instead of second. So there we go. We want L1, L2, and now it's giving me this model. And notice how the model is set up. It's A plus B times the natural log of x. So we're going to fill in these values. So y equals, our a value is 218.862. Our b value is negative, so we're going to subtract 47.807 times the natural log of x. So you cannot tell which model's better by just looking at the models themselves. We have to compare these r values. So this model has an r squared of 0.9982, and it's got an r value of negative 9991. If you do want to take the time to calculate the SSEs, I've done that for you. It just takes a really long time to do. So I'm going to write these down for you as well. So no matter which one of these three metrics we look at, we can see that the logarithmic model explains more of the error. It's got a bigger r squared value, so it's better. The r value is even better. They both have negative relationships, but this has a much stronger relationship than this model. So it wins on this metric. For the sum of squared errors, you want the lowest error. So this guy's got the lowest error. So in all three cases, the logarithmic model is better. You only need to look at one of these metrics. So this is the better model. So the only way you can tell this is to build the model and look at their r value or r squared value.